What I wanted to do to begin with is to give you an overview, thanks Rayhan, an overview of everything that we will be doing in mechanics. Because sometimes people think mechanics is this topic that's like, oh, and then there's this, and then there's this, and then there's this thing, and it gets bigger and bigger, and people kind of forget what it's actually all about. All that mechanics is about, really, is about how things are moving and different forces and how the two things interrelate to each other. So the things that we will be looking at, and I'm not going to read through this in detail, is we will be looking at things to do with forces and how things move. You've already started doing some of this in year 12, but we're now going to be changing it so we have some forces that are acting at angles as well, okay? Things that we need to notice here is forces can be considered as vectors. We talk about magnitudes of force vectors to get the size of the force. That's what we were just looking at. And we often consider forces in different directions because that will help us to work out what resultant forces are. We then might look at some kind of situations where we have things that are connected together like this. I'm sure you've seen some of those scenarios with things on a pulley. We're going to make that a little bit more year 13, and we're going to have some things happening at angles as well. The other thing that we talk about is motion, and you'll have seen at year 12 you did some of these distance time graphs and speed time graphs, and from those graphs, out of those graphs, you should have seen how the Suvat graphs are related to those as well. So not the Suvat graphs, but the Suvat formulae are actually related to those things. And then all of these things are with constant acceleration. There's only one last thing that we look at is when acceleration is not constant. That's the topic where you differentiate things and you integrate things to find out what kinds of distances or displacements or things that it gives you. And the sort of this crucial thing that takes us in between these things is if we know something about forces, we can know something about its motion because of Newton's second law, which is F equals ma. Okay, this is going to be this is basically the entire of mechanics that you will do across this year and last year, just in a page. It is just about forces, it is about how things move, and it's about Suvat and then variable acceleration. That is all of mechanics completely done. Okay, in year 13, we will have things moving at angles, We will have more stuff to do with Suvat in 2 dimensions, so now throwing things rather than things just going up and down. And variable acceleration, instead of it being polynomials like we have down here, we will start adding in like trig or ln functions or e functions, but you know how to differentiate them and you know how to integrate them, so it's no different. So it's actually quite a nice topic, the mechanics, because it reinforces lots of things we've done in pure. Yes?
Will you print that out or something?
Yeah, no, this is from the year 12 one already, actually. This is something that's from the year 12 lesson, but I just thought I'd show it to you at the start just to give you a bit of an overview, because sometimes it feels quite overwhelming that there's a lot of things in mechanics, but actually there isn't many things. We're either looking at forces, we're looking at Suvat, or we're looking at variable acceleration. That's pretty much the whole of what the course looks like. So what we're going to do in this first topic that we've got here is we're going to be thinking about how we resolve components of forces. That's the thing I was just saying that's new in year 13, taking a force that's acting at an angle, like this one that we've got here, and working about how we can deal with things that are happening at angles. We're going to look at things that are on inclined planes, a plane meaning a flat surface, and we're going to look at how things move if they are on an inclined plane. But this is still just forces that we're talking about. We then, later on in this topic, will be thinking about friction, and that's in a separate booklet of things that I've got for you as well. And we just start to see things that all kind of look quite similar to each other. But we're trying to find unknown forces here for when something is in equilibrium, when it's not moving, or when it's moving at constant velocity. Again, we've got more problems to do with statics, meaning things not moving. We then look at things that are moving, and we look at connected particles. Basically, we look at forces and we look at F equals ma, but we're just going to build up really, really slowly. So let's get started with some of these things, which is I made this document for the further math students. I call it the Mechanics Essentials, and I just wanted to go over these things in case there's anything that feels like it's missing. If you want the full version of this document, it's on the Padlet as well. It's just the first thing that's in mechanics, and I had to do this with the further math students. We just did one lesson on like these are the basics, so we could do some of the other things. So some key things here, and I apologise if you do know these things, and if you don't, this is a nice recap. The weight of something is different to the mass of something. It is the mass times g, where g is the acceleration due to gravity. In Edexcel, we say that g is 9.8. Sometimes they will say take g to be 10. okay? But actually it could be even more accurate than 9.8. You could say 9.81, you could even say more accurate than that. But if you do physics, don't use 9.81, we use 9.8 in Edexcel. And weight acts vertically downwards. I've said this is obviously, but I guarantee when we do some diagrams later, especially when we have things on slopes like this, some people will do their weight coming like this, which is obviously going to make no sense at all, because we know that when you're stood on Earth, your weight is always pulling you directly downwards. I've then got some other things about forces. Again, this is stuff you should know, so if you know it, just feel quite happy. The normal reaction, which is sometimes called the contact force, is the force which acts on a box or particle from the surface that it's on. It's called the normal reaction, which I've underlined, which I've made bold, because it acts normal to the surface. And remember, normal means perpendicular. Notice in this diagram how the normal reaction is not going vertically upwards, but it's actually kind of going perpendicular to the surface. It is called a normal reaction because it has reacted to the forces in the opposing direction. You're all feeling, on the chairs that you're sat on, you're feeling a force on your backside pushing you up so that you don't fall through the chair. And that force that you are feeling is the normal reaction from the chair. I'm feeling the normal reaction on my feet from the floor, which is pushing me upwards and stopping me falling down into the first floor, okay? For example, oh, here it is. I've even written it down. When you're sat on a chair, your weight acts down, but the chair, the surface, has a reaction force upwards, which stops you falling to the floor. This is the normal reaction, and we use the letter R for the normal reaction. Sometimes you might see the letter N being used for the normal reaction as well. It can be a bit confusing, but there's so many letters, we run out of letters pretty quickly. I've said here, note that the weight acts vertically downwards, but the normal reaction is perpendicular to the slope. Don't be that person who draws these diagrams wrong when we start doing things on slopes. Okay, someone is going to do it. Just hope it's not you. Okay, we're then going to talk about Newton's first law. Don't have to know that it's called Newton's first law, but it's nice to know some of these extra things about Isaac Newton. An object will remain at rest or will continue to move with constant velocity unless acted upon by an external force. Essentially, this means that something will not move or move with no acceleration if there is no overall resultant force. It means that all the forces are balanced, and we call this equilibrium. And I said to think of the word equal. The thing that's most important here is it's when something is not moving or when something is moving with no acceleration. If it's got no acceleration, what could we say about its speed? Okay, so if it has constant speed, then it is in equilibrium and there are no other forces that are acting. I know this is pretty straightforward, particularly if there are people that do physics in here, but I want everyone to be on exactly the same page. So from this diagram that I made, I've said given that this particle is at rest, work out the value of P and R. Well, clearly, R must be equal to 2g, which is the weight, because it's not moving and they must be equal. And P must be equal to 10 because it's in equilibrium. Forces left equal forces right, forces up equal forces down. You might sometimes see in textbooks, they might say R minus 2g equals 0, which is the same thing as saying R equals 2g. Sometimes they will say all the forces going up and then they make those ones negative. I like saying left and right are equal to each other and up and down are equal to each other as well. And now we're getting on to the stuff that's actually the year 13 kind of content that we've got here, okay? I have written in this orange box that forces can be considered by resolving them or splitting them into two perpendicular forces. The reason we do two perpendicular forces is because perpendicular forces do not interact with each other. If you imagine wanting to move something up and down, you can pull it left and right as much as you like. It's never going to make the thing move up and down. Up and down does not interact with left and right. If you wanted to move it up and down, you could move it left and up. You could move it diagonally, but that's no longer perpendicular. You've made it a combination of these two forces. So these triangles that we have here, which we can split into these two components, they obey the rules of SOHCAHTOA and Pythagoras because they are right-angled triangles. We can split these forces up. So very quickly, using your idea of SOHCAHTOA, I just want you to think about what these sides would be. So maybe this side over here, which is x, I've got that the force is 6 newtons and the angle is theta. Which would I be using out of SOHCAHTOA and cos? So I would have that the cos of theta is equal to the adjacent over the hypotenuse. So 6 cos theta is x. So I can say that along the bottom, this one is 6 cos theta. I'm just going to give you a couple of minutes to quickly decide what you think these forces should be in the different sides of the triangle. After you've done that, what's the pattern that connects them all together? Just going to literally give you maybe a minute, maybe a minute and a half. So you're using SOHCAHTOA to find those missing sides of the triangles and talk to each other about it.
So which, can we pick any side?
Any sides, yep. I want all of the sides of the triangles found. This 6 cos theta is just for this one here. Yeah. Yes, please. Yeah. If you have done these really quick because you've done physics, have a look through the booklet, get a sense of what's going to be coming up in this topic as well. Okay, just 20 seconds more on those. It looks like most people are nearly finished.
So,
Yes.
we've done this before, haven't we?
Yes, you have. You've done some of those things before, not all of them. Okay, so this one running along the bottom was 6 cos theta. What's this one running up the side like this? 6 sine theta, because it's the opposite and the hypotenuse. When you rearrange that, you end up with 6 sine theta. Notice the way that I've drawn my arrows. Something that is pulling in this diagonal force upwards is a combination of a pulling force to the right and a combination of a pulling force upwards. It does 2 of those things together. Also notice, tying back into what we've done with vectors, this 6 newtons here is the resultant vector of 6 cos theta plus 6 sine theta. So it's all tying back into vectors that we have. What about this one running along the top of the 10 newtons one? 10 cos theta, and so then the other one is 10 sine theta. Pretty quickly down here, this one running along the bottom. Good, 12 cos theta and 12 sine theta. And so for this general one that we have here, f, along this bottom part is f cos theta, and f sine theta is along this side here. Now, this bit, you wouldn't do that again, okay? You're not going to do this again. I don't want you to do this again. What I want you to do is to think about the tip that I've written. If f is the magnitude or the hypotenuse, use f cos theta for the side adjacent to the angle. Cos is to do with adjacent, so it's always going to be right next to the angle. Sine is to do with the opposite, so it's always going to be opposite the angle. So very quickly now, we should be able to see when we have a line and an angle, we should very quickly be able to break it down into 2 pieces, okay? This is now going to simplify problems which previously were not able to be solved because they were at angles. We can now break them down into just up and down questions and left and right questions. That blue box down there is really, really important. So we are going to look at a little subtopic of this, and it is called statics. Statics, if you say that something is static, we mean that it is not moving. So we're going to be looking at particles which are not moving. Particles meaning things with mass that have a very small amount of concentrated space. So I've written here, static means there is no movement. This means there is no acceleration, so the particle is in equilibrium. All the forces are balanced in any direction. Forces left equal forces right, forces up equal forces down. Although we do left and right and up and down, if you really wanted to, you could find out the forces in this direction and the forces in this direction, and they would also be equal to each other. In any direction, if something is not moving, the forces are equal. But the easiest thing to do is to do left and right and up and down. So I'm going to take my other forces that I've got here. I'm going to take this P force that I've got to begin with, and I'm going to break it down into its 2 forces. Notice it's going upwards, so I'm going to be going acrosswards and upwards. It's a combination of those 2 things that we have. Muzakir, what's this force running along the bottom here? What would this force be for this triangle that we've got here? Would it be with cos or sine?
Cos theta.
Cos theta, and in this case it's a 30, and the hypotenuse is p, so it's p cos 30. Hisham, what would this one here be?
Sine because of tan 30.
Good, so it's going to be sine 30, but with the length of the line is p, so it's p sine 30 that we've got there, okay? This one that we have here, Tanvir, what could I do for this one if I was going to split it into this force and this force? Good. This one running adjacent to it is for cos 45, and this one is good for sine 45. It doesn't actually matter with 45 because we know that cos 45 and sine 45 are equal because of our cofunction identity. Remember I had that on the sheet for you? Now what I always recommend that we do here, and I got this from one of my students 7 years ago, and she's now a maths teacher, and she always used to take this diagram and she would redraw the diagram, and she'd often do it with a box so you could fit more things coming out of this, and all we would then do is extract the information from this quite confusing looking diagram and make it into a really simple looking diagram. So I'm first of all going to deal with what forces do I have coming out to the right. I have P cos 30. What forces do I have going up? I have P sine 30 and I have 4 sine 45. Notice how both of those forces are going in the upwards direction. Masuma, what do I have going to the left? I have 4 cos 45. And then coming down, I have Q. That's the only one that I've got going down. This diagram is so much nicer to work with than this diagram that we have at the top. Yeah, Mizukir?
So then QB is 4 sine 45 plus P sine 45.
Good. Q is going to be these two forces, but I wouldn't actually look up and down first. Why would I not look up and down first? Yeah, because I've got Q and P here. So I actually think what we're better to do is we're going to resolve, and we're going to resolve in the left and right direction. This letter R means resolve. All it means is to look at those forces in that direction. It doesn't mean resultant. It kind of means resultant, but we're not going to look at it in that way. We're going to resolve in the left and right direction and say that 4 cos 45 is equal to P cos 30. So solving that equation on our calculator and doing 4 cos 45 So we can just go straight in with calculators for this because we want to, it's always going to be numbers at the end of it anyway. We come up that P is 4 root 6 over 3 when you just divide by cos 30, which is 3.27 newtons to 3 significant figures. What you might like to do though is just write a few extra numbers in case we're going to use it later on in the question, because we are going to use it later on in the question. So I always like to write down a few extra numbers because that might be helpful. You can store it if you want to, yeah, or you can just remember that one. The second thing that we're going to do, maybe I'll do a little bit more space. We're going to resolve it now in the upwards and downwards direction. So now we're going to do what Muzakir said. Muzakir said that Q is equal to these two forces, which is 4 sine 45 plus P sine 30. And we know what P is, so Q is going to be equal to 4 sine 45 plus 3.2659. If you want to do that version or that version, sine 30. But remember, we're going to be rounding it at the end anyway, so it doesn't matter so much. Okay, I trust you, but I'm just doing it as well so that I'm doing it at the same pace. And so we get Q is 4.46 newtons to 3 significant figures. Always do your answers to 3 significant figures, or you can even do them to 2 significant figures. The advantage of doing 2 significant figures is if you've used a rounded version earlier on, you can then round it again, and it usually should give you like the correct answer for the ending bit. Okay? So the most important thing, I think, is this. Okay? some of my students in the past very quickly think, I don't need that diagram. And then they make mistakes. I then have some students who always do this diagram, and they never make mistakes. And then they really enjoy mechanics because they're starting to see that they're very successful at it. So I think on the next page of this bit, I've got some questions for you to try on this. Oh, I've got one more example that I'm going to do with you, and then there's going to be some practice for you guys, okay? What you can do on the next example is you can start drawing on some of those angles, because I know a few people are just finishing off writing this one on the board down. You can start resolving those angles for me, those forces. Okay. So a further example that we've got here. You might find using different coloured pens can be quite useful for these kinds of questions. I'm going to start off with, which force do you want me to start with, Zadia? Q. Okay, so I'm going to split Q up into this force and this force. Notice how I always put arrowheads on them. I don't just do lines. I always put an arrow. And so running along the side, I've got Q sine or cos along here. Q cos 30 and Q sine 30. The 12 now needs to be split up as well. The 12 is going to be split into an alongwards force and a downwards force. What's this one up at the top here? Good, so it's a 12 cos 50 because it's running adjacent. And this one coming down must be 12 sine 50. I'm going to use another colour. The 6 needs to be split. Hisham, what should this one running along the bottom be? Good, 6 cos 40, which means coming upwards is 6 sine 40. Please draw heads on the arrows, okay? Please tell me which direction the arrows are going in. Don't just draw the sides of the triangles. Now this triangle, this diagram, sorry, is a mess. There's so much going on in this diagram, it's a complete mess. So what I'm going to do is quite a large box where I know I can fit lots of things in. And I'm going to start writing down all of the forces that we've got. I'm going to give you a second to finish drawing those, and we're going to then start thinking about what we've got here. I'm looking around the room. I'm seeing some people who have already done this question without doing the extra diagram. Let's hope they've not made any mistakes.
So if we get a negative force.
Have I got something with a negative force?
No,
Yes.
I've got a negative force.
Yeah, there could be something with a negative force, because I made this question up. It could easily have a negative force, which means I've done something a bit silly on my diagram.
Yeah, I've got Q as -3. No.
Have you got R, though?
No, not yet. You can work out later. Well, personally, because you got two variables in the up and down, so I did left and right to get Q.
Yeah.
Then
I
I
see what's
swapped
happened.
it.
Yeah. I think I actually need to change something on this question then.
Yeah, you get negative.
I want to change, I don't think that should have been a 6. Let's change this to a 16 instead. So if you change that to a 16, it's then going to fix the question. I think I must have copied that one out wrong when I stole it from a book.
So, you're here.
Yes.
So you have the 12 and you have the Q.
Yep.
So they both go this way.
Yes.
Do you consider both of them?
You have to consider both of them separately, this blue one and this red one separately. Okay, so Khadija, what forces do I have that are going to the right? What forces do I have coming out the right here? Q cos 30 and another one? Good, and 12 cos 50. Yamin, what forces do I have going downwards? This one hasn't actually got any weight, this one. I've not got any weight. Pardon? No. R is just another force that we've got here. This is just the force R and Q. This doesn't have any weight. Because weight is not always equal to the normal reaction. Good, so I've already got that one coming down here. It's the 12 sine 50. Forces going to the left, Muzakir?
16 cos 40.
16 cos 40. Good, I changed it to 16 because I made that one wrong. And then forces going up.
16 sin 40 and Q sin 30.
Okay, we've got R. We've also got
Oh, no, yeah.
16 sine 40, and we've also got Q sine 30. What do you notice about all the colours I've used and what things you should see on the diagram? What do you notice about this diagram here and the colours? The colours are perpendicular to each other, and there should be two of each colour. Because if you've resolved something into two forces, there should be two of them. Lots of people will put one of them in and then might forget, and they might not have this one here. They might just have not looked properly on their diagram. Now all we need to do is to solve this equation. I like it if you can tell me what you're doing to begin with. So you can say you're going to resolve in left and right direction first. So 16 cos 40 equals 12 cos 50 plus q cos 30. So solving that equation, you do 16 cos 40 minus 12 cos 50, all divided by cos 30. Have I still got another negative for q?
For R, it goes to R. So Q is 5.25.
That's
And then R becomes negative.
okay. R being negative is a lot easier to deal with.
But then the resultant forces, so it's going on the ceiling, isn't it?
This isn't modelling anything. This is just a force diagram. So we get that Q is 5.25 newtons, which was actually 5.24610, in case we need that. So this one also is not going to work so well, but that's not a problem.
Now, up and down.
If we now resolve in the up and down, we get R plus 16 sine 40 plus Q sine 30 equals 12 sine 50. So R is equal to
12 sine 50 minus
12 sine 50 minus 16
11.
sine 40 minus Q sine 30. And we get minus 3.715. But that's okay, I'm happy with this, because I have to be. So we've got minus 3.72 newtons. Now, what do you think that actually is telling us about the diagram and R?
The reaction force is...
This isn't a reaction force. This just happens to have the letter R.
That's a force going downwards.
It's actually a force going downwards. So what this actually tells me is our original diagram with R coming up like this. Actually, R is coming down. Q is coming up like this still. We still have the 12 going like this, and we still have the 16 that's going out like this. So if you do ever get a negative answer for a force, it means that the diagram has it in the wrong place, and it should be in the opposite direction to what we had. So actually, I'm pretty pleased that this came out as negative. This is not, can I just say this one more time? This is not a particle sat on a table. This is almost like a bird's eye view of a particle being pulled around in different directions. This is not a normal reaction. I just picked the letter R and I now regret it. Okay? Muzuki.
So with the, you know, next to the 50 degrees, the side comes to the right.
This bit here, yeah.
So would Q cos 30 be equivalent to 12 cos 50?
No, not at all. Because the only thing that is true is these two forces added together equal this. These don't have to be equal to each other. This could be a very small force. Okay? So you've got, on the next page, you have got 3 questions here, and I want to see the second diagram drawn, and you need to find out the value of P and Q. You've then also got 3 more here, and you've got the answers as well for those values. So I need to see your second diagrams for these. Off you go.